Alrighty. Good morning, everybody. So I don't really have much in terms of announcements. The test just ended. Um, we haven't really discussed. Me and the other instructors haven't really discussed what would be on test test number 5. So 4 down, 1 to go, except for that big one. And my best guess is that it'll involve go up to and including definitely 1.8. Perhaps part of, if not all of 4.9, depending on how far everybody gets kind of by the end of this week. So, in case you're looking for a preview, obviously, as always, the exact cutoffs will be covered on or be posted on UMLearn. Alrighty. So there's a question on your screen, as there has been. Feel free to get started with that. It's just one more example that we're going to do, and then we're going to jump into kind of the more theoretical aspects of the course. Sorry about that. All right. So, is the test over and all the section? Yeah. Test 4 anyway. Yeah, it would be over. So if anyone does have any questions about test 4, feel free to let me know. I messed up in my other class by writing down the point wrong. So make sure I get that one right today. All right, so there's 2 ways this question asks us to do it. To use Chapter 1 methods, and then to use Section 3.5 methods in order to find the general form. So we already know how to find the parametric, and at least hopefully we know, or yesterday, or the test 4 wouldn't have gone very well, but how to find the parametric or vector equations of a plane. So in here we want to talk about how to find the general form of a plane passing through 3 points. So one way is to use the annoying way, and one way is to use Section 3.5. So which one do you want to start with? The annoying way, or to do Section 3.5? Sounds good. Annoying way, annoying way, annoying way wins. All right, so we want to find our equation in general form. So we want to solve for A, B, C, and D. We want to find those coefficients and the constant as well. So using a system of linear equations, what can we do in order to find A, B, C, and D? Substitute the points given, right? We want to solve for A, B, C, and D that pass through these points. So what does it mean for the point 1, 2, 3 to be on that plane? What does it mean for the, algebraically speaking, what does it mean for that point to be on the plane? Yeah. X equals 1, Y equals 2, Z equals 3 satisfies the equation. So we get A plus 2B plus 3C plus D is equal to 0. Because X equals 1, Y equals 2, Z equals 3 satisfies the equation. Same thing with the second point. D always stays as D. Same thing with the third point. And now we're looking for A, B, C, and D, which satisfies all three of these equations. That's a system of linear equations with three equations with four unknowns, which can be in, something we can certainly do. And we just solve it using our typical chapter 1 methods. Our REF, whatever works. And now it's just a system of equations where we're solving for A, B, C, and D. All right. We'll blast through the calculations, of course, but any questions about the ideas here? Because actually doing this is stuff from chapter 1 to almost 3 chapters ago. All right. So row 3 is row 3 minus row 1. So 1, 2, 3, 1, 0, 0, negative 1, negative 2, negative 1, 0. 0, negative 4, 1 minus 3 is negative 2, 1 minus 1 is 0. Row 2 becomes negative row 2. As always, of course, your row operations might not be the same as my row operation. That's fine as long as they are appropriate elementary row operations. We are good to go. Negative 4, negative 2, 0. Row 1, subtracting 2, row 2, row 3, adding 4, row 2. 1, 0, negative 1, 0. That's not true. Negative 1. 0, 1, 2, 1. And 0, 0. Negative 2 plus 4 times 2 is 6. 0 plus 4 is 4. Row 3 is row 3 divided by 6. Again, we can get a bit more creative with our row operations. Probably not that step, but in general, we could. 0, 0, 1. Can't avoid the fraction here. At least not nicely. And then row 1 plus row 3 and row 2 minus 2 row 3. Oops. 0, 0, negative a third, 0. 0, 1, 0, a negative a third. 0, 0, 1, 2/3. And we get our matrix into reduced row echelon form. All right, so any questions about the matrix stuff? All right, D equals T, C equals, or C plus 2/3 D tells us C equals to negative 2/3 T. B minus a third D tells us B is equal to a third D, or T, and A minus a third, same thing. A is equal to a third T. So in other words, our equation, with one exception, our equation is going to be 1/3 T x plus a third T y plus negative 2/3 T z plus T is equal to 0. Which looks really weird, but we'll make it a bit better in just a second. All right, so any questions about how we do this? And if not, what value of T makes this not work? Because there is one value of T for which this is not the equation of a plane. So what value of T is this not an equation of a plane? And barely an equation at all. Yeah. Yeah, so for T not equal to 0. A, B, C, and D all being 0 makes this true. It certainly makes it true, but it's not the equation of a plane. It's 0 equals 0, which has every x, y, and z to be a solution. So t equals 0 is not going to work here. And if t is not equal to 0, what can we do to both sides of this equation? T is not equal to 0, what can we do with it? Yeah, we can divide by it. We can certainly factor it out, but since t cannot be equal to 0, we can also divide by it, and we get a much more familiar looking equation of a plane that doesn't have any extra t's in it. We get something like this. So this is certainly doable. Obviously, it gets a little bit annoying with the calculations, but it certainly works. And we can use systems of equations to find the plane passing through 3 points. But man, do we have an easier way. Why did we divide by t? Because it doesn't need to be there. Right? We're used to seeing equations of a plane ax plus by plus cz plus d equals 0, where a, b, c, and d are numbers. Right? Not based off of a parameter. And so we get rid of the t because it's not really necessary. And since it's not 0, we're allowed to divide by it. Technically, we don't have to. This would be the equation of a plane for any t other than 0. But it just looks awful. All right. Now, there was somebody who was really wanting to use 3.5 methods. So how can we use our methods from this section to do this so much more easily? Not using 35. Lost my decimal. What can we do to find 3 of these 4 variables almost right away? How can we find A, B, and C using our ideas from 3.5, aka the cross product stuff? Oh no. I fell asleep. So if we have our general form of a plane, what is the vector ABC? Geometrically speaking, it's the normal vector. ABC is the normal, or is a normal, I guess, is a normal, and as people are saying, we can, the normal to the plane, and we can find the normal as PQ crossed with PR. So PQ, again, same points. We're not changing the points. PQ is going to be 1, 1, 1. We've seen that, how to find PQ and PR quite a bit. PR, I've already forgotten the points, would be 0, -4, -2. Yep. And so N would be the cross product. In other words, IJK 1, 1, 1, 0, -4 should be -2. And we can find 3 of them, not all 4 constants, of course. D still has to be dealt with in a different way, but we can find at least A, B, and C. So that's I, 1, 1, -4, -2, minus J, 1, 1, 0, -2, plus K, 1, 1, 0, -4. So that's what, -2 plus 4, that's 2I, or minus J times -2 plus K times -4. In other words, we get 2, 2, negative 4. Which, as we always have done, we can check by taking the dot product with both of these vectors and verify that they're both equal to 0. All right. So any questions about how we can find our normal vector using cross product methods? All right, so that means we get 2x plus 2y minus 4z, but this didn't find d, so how can we find d? How can we find d? Plug in any of our points. So for example, we can plug in p. There's nothing special about p. If you wanted to plug in q or r, we could have done that as well. If we plug in p, we get 0 is equal to 2 times 1 plus 2 times 2 minus 4 times 3. Be careful, a classic mistake here is to plug in 1, 1, 1. Why would it be wrong to plug in the 1, 1, 1 we had before? Yeah, that wasn't the point. That was the vector parallel to the plane, not the point on the plane. I mean, d equals 0 is a perfectly fine answer. I mean, it's not right in this case, but it's not immediately wrong either. In this case, we get something different. But yeah, classic mistake is to plug in the vector that we got. But the vector is parallel to the plane. It's not a point on the plane. All right, and so we get 2x plus 2y minus 4z plus 6 is equal to 0. We get the exact same plane, just using different methods, and in my opinion, a fairly quicker and easier method to work with. Granted, it requires knowing the connection between the normal and the equation. All right, any questions about this or any of this stuff involving the cross product? All right, are these equations the same? They don't look the same. That's not what we got. It was 1/3 x plus 1/3 y minus 2/3 z plus 1 equals 0. Yeah, so just a note, they don't look the same, but they are the same. It's just the other equation divided by 6. So they are the same equation. You can go back and forth between them, either by multiplying by 6 or dividing by 6. It's not going to change the point. As we know with our elementary row operations, you can multiply any equation or any row by a non-zero number, and you're not changing the solution. So yes, they are in fact the same, even if they don't look exactly the same. All right, so any questions about this Chapter 3 stuff before we move on? Fortunately, not move on to Chapter 4, but that's where the order of the course gets a little bit crazy. All right, so that brings us to sections 1.8 and 4.9. I'm really going to treat them like they're together. For the most part, I'll follow 1.8 then 4.9 just to keep everything straight. But in reality, they belong together. So we'll see a lot of stuff kind of, if you look in the textbook, some of the stuff in 1.8 and 4.9 are effectively the same thing. So everything I'm doing is kind of looking into 4.9, even though what we're doing today is all stuff that you would see in 1.8. But in reality, there's very little difference between the sections. Only just kind of the point of view, not the actual work. All right, so full disclosure before we get started, I just want to kind of give you an idea. So we've spent a lot of time in this course, and I know students grumble about it, but it is what it is, talking about the theory and that kind of stuff. The reason why I really wanted to focus on the theory is because now the course is going to get a bit more theoretical, just in general in terms of stuff. So hopefully all that stuff that we saw, it's not scary because we've been practicing it since the very beginning of the course. And so a lot of the ideas we've been talking about and seeing when we talked about how to show properties are true are things that are going to be important now. So hopefully you've been paying attention. That being said, I'll do my best to try and keep it as grounded as possible. But in reality, I mean, some of these things just get a bit more complicated. So just as a warning, and I'm not meaning to try and scare anybody, but, this is really why we've been focusing on the theory, is to try and get us prepared for some of this later stuff. So that being said, when we're talking about these things, so these two sections, which I'll almost kind of call a mini chapter, is something called a linear transformation. But a linear transformation, and we'll forget about linear for just a second, a transformation is really just a function. So the majority of where we're going to start with this kind of stuff is the same things we would do with functions. But there's one slight difference between a function and a transformation. Does anybody know what the difference is between a function and a transformation? No, both transformations and functions have a range. Same thing. Functions and transformations both have a codomain. I mean, think back to high school, or if anyone who's taken calculus so far, you would have talked about this in calculus as well. What comes out of a function? You can put things into a function, but what always seems to come out of a function? One output. And usually we think of that output as being a number. So the main difference, even though you can define functions in a slightly different way, but as for what most students at this level would think of as a function, is that you put maybe a number, maybe multiple numbers into a function, and you get a number out of it. In this class, we're not getting a number out of it. What are we getting out of a function? What's the output of a function, of a transformation? A vector. And that's the main difference. So even though what we're doing is going to be more complicated, I'm not saying it's as simple as a function, a lot of what we're really doing is the same things we would do for a function. Now we're just doing it for a vector. And that's really what transformations are all about. Stick a vector in, get a vector out, just like you would do with numbers for a function. Which means, just like a function, we can talk about its range, we can talk about its domain, we can talk about something else that we'll get in just a second. Because it's all coming from the same thing that we would do for a function. So, in general, when I say T is a transformation from Rn to Rm, we're talking about the vectors going into it have n components, the vectors coming out of it could have m components, so they don't have to be the same. They might be, but they don't have to be. So in general, what's the domain going to be for this function? Because it really is a function. Don't even know why, really, we give it another name. There's a reason. It's a geometric reason. So what would be the domain of a transformation from Rn to Rm? And it shouldn't be complicated. Yeah, it's just Rn. The domain is going to be whatever the inputs are. The domain is what you stick, all the things you can stick into a function. Beautiful. What's the range? One person saying Rm. Getting some different answers here. A subset of one of those. Which one? I like that one. Which one? Rn or Rm? I mean, in general, what is a range of a function? Yeah, it's the classic mistake to make here. It's an understandable mistake, is to say it's Rm. The domain is the inputs. The range is the outputs. Right? The range is the outputs. So why isn't it just Rm? Aren't the outputs in Rm? Aren't the outputs in Rm? Right, exactly. So a range is always a harder question to answer, usually a harder question to answer than a domain because it depends on what the function is, right? You can't really talk about the range without really talking about what the function would be. There's no magic rule like polynomials. The domain of all polynomials is all real numbers, but you couldn't say the range of all polynomials is all real numbers. I mean, it depends on which polynomial you're talking about. So the range is not what we're really talking about here. We're talking about something called the codomain. So the domain is Rn. The codomain is Rm, and the range depends on the function. So it's not something, or I guess not function here, transformation. It's not something we can answer generally. So the range and the codomain might be the same, but they don't have to be the same. All right. So any questions about what it means to be the domain, to be the range, to be the codomain? And by the way, these are the same words we would use for functions as well. So there's no difference here. All right, so as we get going forward with this, just a notational note, we've been writing kind of x with an arrow to mean a vector. At this point here, there's going to be some times we're going to be, because we're going to talk about matrix multiplication and stuff like that, where it'll be advantageous for us to think of x as being a column matrix. So we're not really going to distinguish between the two. When it makes sense, we'll think of this thing as being a vector. When it makes sense, we'll think of it as being a column matrix. So if we wrote A times X, then X is a column matrix. Other times we might write it. We're not going to worry about the difference between what we're doing here. Everyone's been through at least 2.5 months of linear algebra, so we're not going to worry too much about the distinction between if it looks like a row vector or looks like a column matrix. So just a note, as we move forward, we're going to be seeing this a lot. I'll reinforce that when the time comes. All right, if you have any questions about that, let me know. If not, here's a question right here. Here's some transformation. So for that transformation, determine what the domain is, determine what the codomain is, and compute what t of 1, 3 would be. And all three of these should be fairly quick. These are quickie questions. So what is the domain? What can we stick in to the function? R2. So our domain is R2. Everything we put into this function is a vector with 2 components. It's a vector with 2 components. Our domain is R2. Our codomain. What is our codomain? Where do the outputs live? What land do the outputs live in? They live in R3. Now again, that might be the range. It might not be the range. Right? But for codomain, we're just asking which space do the outputs live. It doesn't necessarily mean that every single thing is the output of some actual vector. The range is always a harder question to answer. We're not asking it here. It is a question that we will be able, in some questions, to answer later. But in general, the range is a much harder question to answer, especially for weirder functions. All right, how do we find t of 1, 3? Again, no different than functions. How do we find t of 1, 3? Plug 1, 3 in for what and where? Which x and y? There's lots of x's and y's. Which one? I see 3 x's and 3 y's. Which ones are we plugging in? Sorry, which one? Yeah, all of them. Right. All of them. So we're plugging in x equals 1 everywhere we had an x. We're plugging y equals 3 everywhere we had a y. Something I always tell my calculus students, it never hurts to put them in a bracket. Sometimes it hurts not to. So I'll stick them all in a bracket, but that becomes 3, 9, and 1 minus 9, negative 8. But that's what transformations are. They're functions. And just like with functions, you can plug numbers in. You plug in the input. The function spits out the output. Same thing for transformations. We can plug in input. The transformation spits out an output. Eventually, like we do with functions, we get geometric interpretations of them. That's where we might go with these transformations. I shouldn't say might. That's where we will go with these transformations. Is, all right, you stick an input into it, we get an output, and what does that output represent? So once we get a handle on how to work with transformations, how to use transformations, eventually we'll talk about what transformations are doing to the vector geometrically. And yes, so in this case, this particular transformation converted a vector in R2 to a vector in R3. That's exactly what it is, yeah. So the domain is the input space, and the codomain is the output space. So we're not saying everything in the codomain is an output, but it's where the outputs belong. So any other questions about what these transformations are really doing? All right. So remember, it wasn't too bad for about 5 minutes. All right, so now we're going to jump to linear transformation. So a transformation is linear. Now, a linear transformation and a linear equation, there's obviously going to be a connection there, but they're not the same thing. So a linear transformation is not a function with linear equations. While there is a connection, it's not exactly the same. So a linear transformation is a transformation that satisfies two major properties. Two major properties. The first property is that it doesn't matter when you add things. You can add the vectors before you plug it in. You can add the vectors after you plug it in, and it doesn't make a difference. Same thing with multiplying by constants. You can do it before or you can do it afterwards. That's what it means to be linear. So we're going to have a bit of a logic game here, because this is probably one of the most confusing parts about what we're going to do. Is we want to show, if it's linear, we want to show that these equations are both true. How can we do that? So before we get to these examples, let's get to the how do we do these kind of things. So here's the big idea of trying to determine whether a transformation is linear or not, because linear transformations are special magical functions that nice things happen, and nonlinear ones are crazy ones that do bad things. So the idea is, how do we show something is special? How do we show that it's linear? So to show t is linear, what do we need to do? Pop the definition back up here. If we wanted to show that something was linear, what do we need to do? We have these two properties. What do we need to do? We need to prove the left-hand side is equal to the right-hand side. Beautiful. Like we saw with our properties. Remember all those properties we saw of matrix multiplication and vector properties. We showed some of those properties were true. That's what we're going to be doing here. The same style of what we did before, we're going to do it here. We're going to show the left-hand side is equal to the right-hand side for... Do we plug in numbers to do that? What do we do? Is that what we did before when we showed the properties? Yeah, where we're leaving things as variables. And as somebody mentioned, we need to show for all. Show for all vectors and constants. And for both properties. So this is how we show something is linear, and it's really going back to the properties we showed of matrices, the properties we showed of vectors. The way we do it is the same way we did those, where we had to take a left-hand side, see what it was. It often turned out to be an ugly expression. We take a look at the right-hand side, see what we get. Again, it could turn out to be an ugly expression, and we want those ugly expressions to be the same in the end. That's how we can show that these two properties are true. So that's the idea of how we show something is linear. On the flip side, to show t is not linear, what do we have to do? So in other words, what is the opposite? How do we show that something is not? We need to show the left-hand side is not equal to the right-hand side for both properties or one property. At least one, which means we only need to do one. Right? If we can show one property fails, we don't care about the other one. Right? So we need to show that at least one of these properties fails, which really means we need to show one of the properties fails. And when how do we show one of these properties fails? Someone said the left-hand side is not equal to the right-hand side, and that's certainly true. Do we have to show the left-hand side is not equal to the right-hand side for all of the vectors? For one of the vectors, can we plug in numbers? Yes, to show it's linear, both have to have the left and right-hand sides equal. So we want to show the left-hand side is not equal to the right-hand side for all of them? So what's the opposite? So we have a statement here. This is true for every single vector. What is the opposite of being true for every vector? Being false for every vector? Right. Being false for at least one vector. So we need to show the left-hand side is not equal to the right-hand side for one, what we call a counter example. For one counter example. So to show it's true, it's an involved process. We need to show both properties are true. We have to keep it general. We have to use the letters. We have to say it's always going, or show it's always going to be true. To show it's not linear, we have to come up with one thing that doesn't work. We need to come up with one example of a vector or vectors where the left-hand side is not equal to the right-hand side for one of the properties, and that's it. So to show it's linear and to show it's not linear is a completely different process. What we do, one of them we keep it general, the other one we plug in numbers. One of them we're showing it's always true, the other one we're showing it's false just once. And so what we do for linear and nonlinear are very, very different things. And so, AKA, it's a bit confusing and certainly requires some practice. Right, but any questions about these logic ideas before we get to jumping into an actual example. Because we're showing things are true or not true. I'll take it. All right, so let's start with our first one. T of xy, the one we were talking about before. T of xy equals x times y squared, x minus y squared. So, our rules for how to show this are very, very different depending on what we're trying to show. So, honestly, we really want to make a guess as to whether we think it's linear or not. And if we're wrong, then we're wrong and we'll figure it out along the way. But we want to make a guess as to whether we think it's linear or think it's not linear first. So do you think this is a linear transformation or not? Again, it can be a guess. Do we think it's linear or do we think it's not linear? And if we're wrong, we're wrong. We'll figure it out along the way. Just a guess. Do you think that's linear or do we think it's not linear? 1, 1. The knots are taken. Oh, now we got 3, 4, 4, 5, 4, 5, 4, 4 tied again. The no's are taking over again. I should have really done a poll. All right, so it looks like more people are saying not than are. That being said, we'll talk about what to do if we choose it wrong. But some people are saying not. All right, so we think it's not. So if we think it's not true, how do we show it's not true? Right, we want to come up with a counterexample. So am I going to be plugging in x1, x2, y1, y2, and all these kind of things? Or u1, u2, v1, v2? No, what are we going to do? If we're going to find a counterexample, what are we going to do? Yeah, plug in some numbers, see what we get. Do we want to show the first property fails or the second property fails? I mean, the answer to all of these things is it doesn't really matter. We could show either one. So let's try and show the property fails. So in other words, we want to let u equal to something with actual numbers, v equal to something with actual numbers, and then hope that property 1 fails. So give me some numbers, or I guess they're vectors. Give me a couple vectors to use. 1, 2 sounds good. Careful, what's the domain of this transformation? What's the domain of this transformation? R2, so if you're giving me something that's not in R2, we got a problem. 3, 4, sounds good. And if anyone's wondering, because it's a natural question, where do these vectors come from? The answer is they came from whatever you feel like coming from. So if we're going to show this is false, and in a class of 170, half people might not know what's going on, but the other ones, the other 80 or so, I would expect to get about 80 different counterexamples. So there's no one counterexample that's going to show this is false. If I see 50 people with the same counterexample, you can probably guess what we're going to be thinking. Of course. Yeah, there's no one way to find a counterexample. Glad I don't have to mark it. And so, now how do we show that property 1 fails for these two vectors? If assuming it does, maybe it'll work, but let's hope that it doesn't. So how do we show property 1 fails? Try one of the conditions. So let me write here, we're going to guess that it's not. And later on, we'll talk about why we make our guesses the way that we do. So we're going to take a look at our left-hand side. So our left-hand side is equal to t of u plus v. So order of operations, what do we do first? Add them together. What's u plus v? 4, 6. Sounds good. And just like we did with t of 1, 3 before, we're going to plug in, I wish these numbers were a bit smaller, but it is what it is, 4 times 6, 4 times 6 squared, 4 minus 6 squared, that's 24, 144, negative 32. Beautiful. There's our left-hand side. Let's go to our right-hand side. T of 1, 2 plus T of 2, 4, 3, 4. T of 1, 2 is what? 2, 4, negative 3. 3, 4 would be 12, 48, and 3 minus 16 is negative 15. And when we add them together, we get 14, 52, and negative 18. And the question, of course, is the left-hand side equal to the right-hand side? No, it's not. So property 1 fails. T is not linear. So if we can show one of the properties fails for one example of vectors, and it didn't have to be property 1, it could have been property 2, but if we can show one of the property fails for one of the vectors, that's enough to say this transformation is not linear, and we don't get all the special stuff that comes out of it. All right, so any questions about how we did this? How we showed that a transformation is not linear? How did we do the right-hand side? Oh, which part? So this is just sticking u and v into the right-hand side. So the very first line was just sticking u and v into the right-hand side. So that's where this came from. Then, just like we did with t of 1, 3 earlier, we plugged x equals 1, y equals 2 into the transformation. Did the same thing for 3, 4. And that's where these ones came from, unless I made an arithmetic mistake. And then we added them together. So as you can probably guess, trying to show it's not linear is going to be a little bit nicer than showing that it is. All right. Now, this is the end of the question. I just want to make a quick little note. Let's say we did this. What if the left-hand side just happened to equal to the right-hand side? What if the left-hand side did equal to the right-hand side? What does that mean? Does that mean property 1 is satisfied? I mean, is it now half linear? It shows property 1 is satisfied for that one point, but does that mean property 1 is satisfied for all points? No. So if you plugged in numbers and you got that property 1 happened to work, then that tells us next to nothing. Really does. It doesn't really tell us anything. If you plug in numbers and got that the property was true, then you might as well have done nothing. Right? It doesn't really do much for us. So you have an option. Maybe that's enough convincing for you to try that it is linear. Maybe you want to try some other points to try and show that it fails. But the point is that you can never plug in numbers to show a property is true. You can plug in numbers to show a property is false, but you can never plug in numbers to show a property is true. It just won't work because it doesn't show it's true for all. You showed it was true for one, and therefore you get 1 out of infinity marks. Figure out what that is. All right. So the answer is we know nothing. Maybe you need a different counterexample. Maybe you want to go and do the other method to try and show it's linear. The point is we know nothing from that information on its own. Where did I get 2, 3, negative 2, 4, negative 3? That we got by plugging in 1 and 2 everywhere we had our xy squared, x minus y squared. And then the same thing for 3, 4. So just like we did with t of 1, 3, we plugged the numbers in, we saw what we got. And then we just added them together in the next line. All right, so plugging in numbers can never be used to show a property is true. Plugging in numbers can only be used to show a property is false. Unless you want to plug in every single possible number. And since there's infinitely many, that could take a while. All right, so let's try the next example. If anyone has any more questions, feel to fire it off. This is perhaps one of the most complicated concepts to wrap our head around in the course. We want to make sure we do our best to kind of understand the ideas. All right, so our second transformation was this. So we start off the same way. Do we think it's linear or do we think it's not linear? So we're going to guess that it's linear. Right. We're going to guess that it's linear. Couple reasons you might want to guess that. People who are guessing that they think it's linear, why is that your guess? That doesn't surprise me. I mean, the last one wasn't linear, so this one's probably linear. Fair enough. Yeah. So for sure, the domain equaling the codomain is true here, but that's not necessarily the case, right? No square roots, powers of 1, those are some good reasons. I mean, not to dismiss some of the other reasons, but that's some good reasons that we might want to make that guess, is that we're not getting any squares, we're not getting any square roots, all the things that make things not lines, we're not seeing them here. That might be a good reason to guess that it's linear. Whereas in the last one, we saw some y squareds. That's a decent guess that it's not. Again, eventually we'll come up with general rules that say, this is how we can tell, this is how we cannot. So we're getting there. But those are some good reasons to make the guesses that we are. All right, so we're going to guess that it's linear, which means we need to show that both properties are true always. So no more plugging in numbers. If you plug in numbers and then conclude that it's linear, then you've got a problem. All right, so we're going to guess that it's linear, so we want to show property 1 is true. What do we got to do? So this will look very much like when we showed those matrix properties. What do we have to do? Right, we're going to show the left-hand side is equal to the right-hand side. The main difference is we're keeping it general. We're not using numbers, we're using variables. That's the big difference. Other than that, we're still looking at the left-hand side and the right-hand side. So instead of letting u equal specific numbers, now we're going to let u equal to u1, u2. Why am I doing u1, u2? Sorry, why am I doing 2 of them, I guess? Why are we doing 2? Right? Because our domain is R2. So instead of doing 1, 2, and 3, 4, we're keeping it general with the letters. Other than that, what we do is the same. Left-hand side, right-hand side. Hopefully, if we want it to be linear, hopefully we'll see that both sides are equal. All right, so any questions about this setup before we start doing some messy little algebra? Hopefully linear algebra. Could we write variables for the previous example as well? First of all, why on earth would you want to? But second of all, I'm going to address that after this, because when we write the stuff down we're about to write, I'll be able to more easily answer that question. Yes, 2 because the domain is R2. All right, so our left-hand side is equal to T of U plus V. So as we did before, we start with adding the vectors together. So that's U1 plus V1, U2 plus V2. So just like our first step on our left-hand side before was adding the specific numbers together, now we're adding the letters together. But we're still doing the addition first. All right, this is probably the most confusing step. What do we do to compute the transformation of this vector right here? Right. So what is the x? So before, when we did t of 1, 3, everybody said x equals 1, y equals 3. Or everybody that plugged things into the chat. X equaled 1, y equaled 3. So what is x and y now? So x is u1 plus v1, y is u2 plus v2. But the idea is still the same. Everywhere we had an x, you're plugging this thing in. Whether it's a number, whether it's an expression, whether it's a smiley face. It doesn't matter. Wherever there was an x, we're plugging that in. And so we get x minus y, u1 plus v1, u2 plus v2. There's our x. There's our y. Same thing with the other one. We're going to be adding it together. u1 plus v1, u2 plus v2. Here's our x, and here's our y. So that's plugging it in, and then because we want to see if it equals the right-hand side, we're going to simplify it up a bit. u1 plus v1 minus u2 minus v2. u1 plus v1 plus u2 plus v2. So there's our left-hand side, and the hope is that the right-hand side gives us the exact same thing. All right, so any questions about how we did the left-hand side here? How did we get this? So here's x, here's y, and what was our transformation? I'll write it here at the bottom. What was t of xy? X minus y, x plus y. So here's x, it goes right there. Here's y, it goes right there, and that's exactly where that line came from. Same thing for the other one. So there's not much more we can do with that one, so we'll jump to the right-hand side. The right-hand side tends to be a bit easier. That's t of u1, u2 plus t of v1, v2. So again, there's our x and our y, so that's u1 minus u2, u1 plus u2, and then v1 minus v2, v1 plus v2, and then we add them together. Add the first components, and add the seconds. So for both the left-hand side and the right-hand side, and if you go back to how we showed matrix properties were true, we did the same thing. Find the left-hand side, find the right-hand side, and in the end, take a look and ask ourselves, are they the same? So in this case, are they the same? Indeed they are. So that means property 1 and property 1, haven't got to property 2 yet. That means property 1 is always true. It didn't just work for one number, didn't just work for one vector. It's always true. And we'll do the same thing with property 2. And if that one is also true, we know that it's linear. Alrighty. But you'll notice very similar things. So that's, I mean, it was nice to know why the matrix properties were true as well, but that's really why we focused on this for matrix properties, so that this wouldn't be the first time you see it. All right. Any questions about how we showed property 1 was true? All right, let me go back to what question somebody asked in the chat a little while ago. Or that this isn't the question they asked, but it will lead to the same ideas. What if these were not the same? What if these were, or let me rephrase that. What if they didn't look the same? What if they didn't look the same? If they don't look the same, does that mean that they're never the same? Like, what if I had on one side x1, y1, x1, y1, and this one we had, let's say, x1 plus y1, x1, y1. They don't look the same, but they could be the same. I mean, the question, so, like in this case here, if they don't look exactly the same, they might be the same and they just don't look like it. Or they might be true sometimes and not other times. So the point is that we can never really use the letters in order to find a counterexample. So if you get the two expressions to not be the same, then you have to be careful with that, because just because they don't look like they're the same doesn't mean that they're not. Anytime you go to the back of the book and your answer is different than what the answer is in the back of the book, it doesn't necessarily mean that your answer is wrong. They could be the same and just not look it. So when somebody asks their question, could we plug in letters for it to show it's false? The answer to that is, if you do that, then not only do you have to make it look like they're not the same, but you have to actually prove that they're not actually the same. And the way you prove they're not actually the same is you plug in numbers. So at some point, you're going to be plugging in numbers anyway. So if you get to the point here where the expressions don't look like they're the same, then you would still plug in numbers to show that they're not actually equal for at least one counterexample. So if you think it's false, just start by plugging in the numbers. You don't have to work with the letters, is kind of the point. All right, where did this second line come from? Same thing as kind of where it came from above. For the first one, here's x, here's y, and we're plugging it into t of xy is x minus y, x plus y. The second line came from the same reasoning as the one from before. All right, any other questions about how we showed property 1 is true? Can't stress it enough. To show it's linear, use letters. To show it's not linear, use numbers, and don't try and mix and match. One way is just never going to work. The other way makes it more complicated than it needs to be. All right, property 2 is actually usually slightly nicer. Same ideas, just slightly nicer in calculations. So again, let u be equal to u1, u2. In this case, we don't need a second vector. C is a number. So T of CU, there's our left-hand side. What is C times U? What is C times U? CU1, CU2. So again, here's our X, there's our Y. So that's equal to x minus y and x plus y. You could actually get creative and then algebraically manipulate this to look like the right-hand side, but I'll just stay consistent and look at our right-hand side. c times t of u1, u2, just like we'll have the same t of u as before. So u1 minus u2, u1 plus u2, and that's cu1 minus cu2. Multiplication is distributive, and that equals our left-hand side. So property 2 is satisfied. So t is linear. This is the idea. Again, I know I've said it 15 times, but why not a 16th? If we're trying to show it's linear, we got to show both properties are true with letters, not specific numbers. Specific numbers can only be used to show it's false if the left-hand side's not equal to the right-hand side. All right. Any questions about how to show something is linear or is not linear? Yeah, we're not going to get to anything specific in 4.9. Yeah, if you want to know the distinction, 1.8 is all about kind of what transformations are, how to work with them, the special stuff that comes out of it. 4.9 is more about examples of linear transformations and the geometry about it if you're looking for a distinction. Yeah. All right. Sounds good. Here's a little tip, though, for your counterexamples. Usually finding counterexamples, if it's not linear, usually finding counterexamples doesn't work. Here's a little tip. Don't use the zero vector for a counterexample. Quite often, and I'm not saying it never works, it does sometimes work, but quite often, zero, even if it's not linear, often the properties will still work for the zero vector. So you can kind of usually waste your time when it comes to using zero as a counterexample. It's not wrong, but often the zero vector makes things work that only work for the zero vector. Unit vectors, go for it. Unit vectors don't tend to make properties magically true that are usually false. All right. So, just one little notational note. There's another way of writing this. So for these two examples that we just did, often you'll see the textbook write it in this way. Oh, I thought I fixed this. Where instead of writing t of x, y equals, and they plug in the little mini functions inside the vector, they'll just say w1, w2, and w3, and then write what those mini functions would be on the outside. So you'll notice that these two things here, these two ways of writing the functions or the transformations are the exact same thing as we wrote before. So sometimes, and often you'll see your textbook doing this, where they won't actually put the x minus y, and x plus y into the vector. They'll just write the functions on the outside. It's the exact same thing. There's no difference between the two. So just as a notational thing, often you'll see it this way. It's the exact same thing. So when picking numbers for counterexamples, just don't use zero. Don't use all zeros. Right? Like for example, if something was x times y, then whether you're multiplying or not, you're going to end up getting zeros a lot, even when they come from different things. Like 0 times 2 and 0 times 3 are the same thing, even though 2 and 3 aren't the same. So we can magically make things equal that shouldn't usually be equal. So it's not a rule. I'm not saying you can't use zero. I'm saying that it often isn't a good choice for a counterexample. All right. So any questions about this notational thing? Again, it's just another way of writing the exact same thing. Instead of putting the functions inside the components, we kind of write the functions outside the components. That's the only difference. All right. So, here's a question here. So I'm telling you, so in this one I'm telling you that this is a linear transformation. I'm not telling you what the transformation is. I'm telling you it's a linear transformation. And I'm telling you three specific things. I'm going to tell you t of 1, 0, 0, t of 0, 1, 0, and t of 0, 0, 1, and I'm telling you t is linear and nothing else. See if you can compute t of 3, -2, and -1. Anyone have an answer? No. I'm telling you it's linear. No, if you wanted to relate this to Math 1500, this would be a question like, let f be a continuous function that satisfies x properties, show something, if you want to relate it to Math 1500. So I'm giving you that it's linear and asking you to show something different. Does this? No. It does not. It would be fun if it did. Now I'm going to try and think of a linear algebra question that does look like that. But no, not this one. Anyone have an answer? All right. Well, okay. So I'm not surprised. It's the idea behind this example, if you're kind of wondering what the motivation of this example is to get used to some of the properties that we're going to be seeing about linear transformations. So we know that this transformation is linear. We're told that. That's a given. We don't have to show it. We're told it. Taking a look at these three things, that's probably not much of a coincidence. What are those three vectors? Yeah, those are our elementary vectors, I, j, and k. These are our elementary vectors. So we're going to see the power of the elementary vectors showing up. Right? We're going to get the power of being linear and the power of being an elementary vector. So call this thing I, call this thing j, call this thing k if you'd like. I'm gonna. All right. But that's not what this vector is. That vector isn't I, that vector isn't j, and that vector isn't k. But we know it's linear, which means if it's linear, then it satisfies a couple properties. What are the properties that it satisfies? All right, we had two properties that it satisfied. Let's put them back up on the screen. It satisfied these first two properties. So, can anyone see a way of just taking the vector, nothing about transformations, just taking the vector and writing it as three specialish vectors added together? Right, we could write it as 3, 0, 0 plus. Now, it's debatable as to why we would want to do this, but I'll give you a reason in a minute. Yeah. Plus 0 to negative 1, or 0, plus 0, 0, negative 1. So as some people are saying, we can write it as t of 3 times 1, 0, 0, minus 2 times 0, 1, 0, minus 1 times 0, 0, 1. And we can write the vector we want as a combination, a linear combination of the vectors we were given, specifically the standard vectors. So if you want to, you could also say that this is 3i, as some people are, minus 2j, minus k. Don't really need that, but we could. So now let's use the fact that it's linear. Since, whether we write it as 1, 0, 0 or I, since it's linear, what does this have to equal? What does this equal because it's linear? And we have those two linear properties. So let's look at that first property. What does the first property say? Not just left-hand side equals right-hand side. But what does that first property say? Right. First property says we can split them all up. We can write this as t of 3i plus t of negative 2j, or the negative can come out as well, plus t of negative k. That's using the property 1. Property 1 says if we add them inside t or add them outside t, it doesn't make a difference. That's property 1. What does property 2 say? That we can take out the constant. So whether we call them I, j, and k, or we call them 1, 0, 0, 0, 1, 0, or 0, 0, 1, the point is we could take 3, negative 2, and negative 1 and write the transformation in terms of what we were given in the original question. In other words, this is 3 times 2, 0, 3, 2, minus 2 times whatever it was. I've already forgotten. 2, 1, minus the last one, negative 2, 1. And whatever that is, what's that? 9 minus 4 plus 2. So 7, 6 minus 1 minus 1, 7, 4. And by 7, 4, I really meant 7, 3. All right. Now, the actual numerical answer here isn't really the point. The point is that we can split this up, which means we only really needed these 3 vectors in order to get all vectors, because everything can be written in terms of that. And I'm already 5 minutes past time, so I apologize. If you have any questions about this, let me know. If not, this is where we're going to be going with this. If we're dealing with a linear transformation, that we can write every single vector in terms of these special ones, these elementary ones, that can give us a way of working with these linear transformations a little bit more nicely. If you have any questions, let me know. If not, have a good day.